Imagine stepping onto Mars. Knowing you will never come back, we talk about colonizing Mars like it's the next vacation spot. But what if the real story is this? Getting there might be possible, but coming back is the part we're not ready for. First, consider the brutal reality of physics. Mars may have weaker gravity than Earth, but escaping it still requires enormous energy. That means rockets, fuel, and precision engineering, all of which would need to already exist on Mars before astronauts even arrive. But how do you get that fuel there? You either carry it, which is massively expensive, or produce it on Mars using technologies that have never been tested at scale in such an extreme environment. Now think about this. On Earth, if something goes wrong, help is hours away. On Mars, help is millions of kilometers away. And communication itself takes minutes. There is no emergency rescue, no backup plan, no second chance. And then there's the environment. Mars is not just cold, it's deadly. Radiation exposure alone can damage human DNA over time. Dust storms can last for weeks. Equipment failures aren't just inconvenient, they're fatal. Even landing is a nightmare. Mars' atmosphere is too thin to slow spacecraft properly, yet thick enough to create intense heat. Engineers call it the 7 minutes of terror. Now imagine doing all of that in reverse to leave the planet. If this makes you rethink space travel, pause for a second and ask yourself, would you take a one-way trip to Mars if it meant becoming part of history? Or is coming home what truly defines exploration? The idea that Mars has weaker gravity often creates the illusion that leaving the planet should be relatively easy, but this assumption hides a much deeper and more demanding reality. Yes, Mars's gravity is only about 38% of Earth's, which means objects weigh less and require less force to lift off the surface. However, escaping a planet is not just about how heavy something feels. It's about reaching escape velocity, the speed required to break free from the planet's gravitational pull entirely. For Mars, that speed is about 5 kilometers per second, which is lower than Earth's 11.2 kilometers per second, but still enormously high in practical terms. Achieving that speed requires powerful rockets, precise engineering, and, most critically, a large amount of fuel. Fuel is where the real challenge begins. On Earth, launching a rocket is supported by a vast industrial network, fuel production plants, transportation systems, testing facilities, and teams of engineers ready to fix any issue. None of that exists on Mars. If astronauts are expected to return, their return vehicle must already be waiting for them on the Martian surface, fully functional and fully fueled. This means either transporting massive amounts of fuel from Earth, which dramatically increases mission cost and complexity, or producing fuel on Mars itself using local resources, a process known as in situ resource utilization. While scientists have proposed methods to create fuel from Martian carbon dioxide and water ice, these systems are still experimental and have never been proven reliable on the scale required for a human return mission. Even if the fuel problem were solved, the rocket itself introduces another layer of difficulty. A Mars ascent vehicle would need to survive months, possibly years, in a harsh environment before it is ever used. Temperatures on Mars can drop to minus 80 degrees Celsius or lower, which can degrade materials, damage electronics, and affect fuel stability. Dust is another major issue. Fine, electrostatic particles can coat surfaces, interfere with mechanical systems, and reduce the efficiency of critical components like solar panels. Unlike on Earth, there is no maintenance crew or supply chain to replace damaged parts. Everything must work perfectly after long-term exposure to these conditions. Timing also plays a crucial role. Launch windows between Mars and Earth occur only about every 26 months, meaning astronauts cannot simply leave whenever they choose. If something delays the launch, whether it's a technical malfunction or an environmental issue, they could be stranded on Mars for years waiting for the next opportunity. This creates immense pressure for every system to function flawlessly within a very narrow time frame. The complexity increases further when considering the sequence of operations required for liftoff. The rocket must ignite successfully, maintain structural integrity during ascent, navigate through the thin but unpredictable Martian atmosphere, and reach the precise trajectory needed to intersect with a spacecraft returning to Earth. Any small error in guidance, propulsion, or timing could result in mission failure. On Earth, such issues can sometimes be corrected mid-flight with real-time communication and support. On Mars, the communication delay makes immediate intervention impossible, forcing astronauts to rely entirely on pre-programmed systems and their own limited ability to troubleshoot under extreme conditions. All of this reveals a critical truth. Leaving Mars is not just a scaled-down version of launching from Earth. It is a completely different challenge, combining the need for self-sufficiency, perfect timing, and flawless engineering in an environment that offers no room for error. The lower gravity may reduce some physical demands, but it does not simplify the broader system required to make a return possible. Instead, it creates a scenario where every dependency, fuel, machinery, timing, and survival must align perfectly, or the opportunity to leave the planet disappears entirely. The absence of refueling stations or any kind of supply chain on Mars is one of the most decisive barriers to returning from the planet, because space travel depends not just on vehicles, but on a continuous flow of resources. On Earth, every launch relies on an enormous logistical network working behind the scenes. Fuel is produced in specialized facilities, transported through pipelines or tankers, stored under controlled conditions, and tested repeatedly before use. There are backups, redundancies, and entire teams dedicated to ensuring that even the smallest detail is correct. Mars has none of this. It is a completely isolated environment where every gram of material must either be brought from Earth or somehow created on site. And both options come with extreme limitations. Transporting fuel from Earth sounds straightforward in theory, but in reality it quickly becomes impractical. Rocket fuel is heavy, and the more fuel you carry, the more fuel you need just to lift that fuel into space. This creates a compounding problem where the mission becomes exponentially larger and more expensive. Sending enough fuel to Mars to support a return journey would require multiple launches from Earth, careful coordination, and precise delivery to the Martian surface. Each additional launch introduces new risks, new costs, and new opportunities for failure. If even one critical shipment fails to arrive or is damaged during landing, the entire return plan could collapse. Because of this, scientists have explored the idea of producing fuel directly on Mars using local resources. The Martian atmosphere is composed mostly of carbon dioxide, and there is evidence of water ice beneath the surface. In theory, these ingredients could be processed to create methane and oxygen, a type of rocket fuel. While this concept is promising, it is still largely experimental. Small-scale demonstrations have shown that it can work in controlled conditions, but scaling it up to produce the tens of tons of fuel needed for a human return mission is an entirely different challenge. The equipment required for this process would need to operate continuously for months or even years without failure in an environment that is hostile to machinery. The reliability of such a system is a major concern. On Earth, industrial systems are constantly monitored and maintained by skilled technicians. Parts are replaced, systems are recalibrated, and unexpected issues are addressed immediately. On Mars, astronauts would have to manage all of this themselves with limited tools, limited spare parts, and limited expertise in every possible system. If a critical component breaks, there is no way to order a replacement or call in a specialist. The entire fuel production system would need to be extraordinarily robust. Yet even the most advanced machines are not immune to wear and failure over time. Storage adds another layer of complexity. Rocket fuel must be kept under specific conditions to remain stable and usable. Extreme temperature fluctuations on Mars can affect both the fuel and the tanks that contain it. If the fuel degrades or leaks, it could become unusable and there would be no way to replace it. This means that not only must the fuel be produced successfully, but it must also be stored safely for an extended period until the launch window arrives. All of these challenges highlight a deeper issue. On Mars, there is no margin for error because there is no support system to fall back on. Every step of the process, from transporting equipment to producing fuel to storing it safely, must work perfectly in sequence. A single weak link can jeopardize the entire mission, turning the idea of a return journey into an unreachable goal. Mars presents a unique and unforgiving challenge when it comes to landing and takeoff, largely because of its atmosphere, or more accurately, the lack of a sufficiently useful one. The Martian atmosphere is about 1% the density of Earth's, which places it in an awkward middle ground that complicates both descent and ascent. On Earth, spacecraft can rely heavily on thick atmospheric drag and large parachutes to slow down during landing. On the Moon, there is no atmosphere at all, so landings depend entirely on controlled rocket thrust. Mars offers neither advantage. Its atmosphere is too thin to provide significant braking, yet thick enough to generate intense heat during entry, forcing engineers to design systems that must handle both aerodynamic stress and propulsion simultaneously. When a spacecraft approaches Mars, it enters the atmosphere at extremely high speeds, often exceeding 20,000 kilometers per hour. The friction with atmospheric particles creates intense heat, requiring a robust heat shield to prevent the vehicle from burning up. However, because the atmosphere is thin, this heat shield does not slow the spacecraft nearly as much as it would on Earth. As a result, the vehicle is still traveling at supersonic speeds, even after enduring extreme heating. At this stage, parachutes can be deployed, but their effectiveness is limited. The thin air cannot generate enough drag to significantly reduce speed, especially for heavier payloads like those required for human missions. This leads to one of the most difficult phases of the entire mission, often referred to by engineers as a critical transition point. The spacecraft must switch from aerodynamic braking to powered descent, using rockets to slow down and land safely. This requires precise timing and flawless coordination between multiple systems. If the parachute deploys too early or too late, or if the engines ignite at the wrong moment, the spacecraft could crash. The margin for error is extremely small. And unlike on Earth, there is no possibility of real-time correction from ground control due to communication delays. For robotic missions, engineers have developed creative solutions to these challenges. For example, NASA has used techniques like sky cranes, where a hovering platform lowers a rover to the surface using cables. While this works for relatively small payloads, scaling such methods up for human missions is far more complex. A crewed lander would be significantly heavier, requiring more powerful systems and introducing additional risks. Every added kilogram increases the difficulty of slowing down and landing safely, pushing current technology to its limits. Takeoff from Mars is equally demanding, though in different ways. While the thin atmosphere reduces aerodynamic drag during ascent, which might seem beneficial, it also means there is less natural stabilization. Rockets must rely entirely on their own guidance systems to maintain the correct trajectory. Any deviation could result in missing the precise path needed to rendezvous with a spacecraft in orbit. This is not just a matter of direction, but also timing, velocity, and positioning, all of which must align perfectly. Align. The ascent vehicle itself must be lightweight, yet powerful enough to achieve the necessary speed to reach orbit. This creates a delicate balance between minimizing mass and maximizing performance. Unlike launches from Earth, where infrastructure supports every stage of preparation, a Mars ascent vehicle would have to operate independently after sitting idle on the surface for an extended period. Its engines, fuel systems, and electronics must remain in perfect condition despite exposure to extreme cold, dust, and radiation. Another complication arises from the unpredictability of the Martian environment. Dust storms can obscure visibility, affect sensor readings, and interfere with mechanical systems. Even minor environmental variations can impact performance, and there is no way to fully simulate these conditions on Earth. This uncertainty adds another layer of risk to both landing and takeoff operations. All of these factors combine to make Mars one of the most difficult places in the solar system for controlled entry and exit. The thin atmosphere, extreme speeds, precise timing requirements, and lack of external support create a scenario where every phase of the journey must be executed with near-perfect accuracy, leaving almost no room for recovery if something goes wrong. One of the most underestimated barriers to returning from Mars is the communication delay between the planet and Earth, which fundamentally changes how missions must operate. Unlike missions in Earth orbit or even on the Moon, where communication is nearly instantaneous, signals traveling between Earth and Mars can take anywhere from about 4 to 24 minutes one way, depending on the relative positions of the two planets. This means that a simple message sent from Mars could take up to 24 minutes to reach Earth, and any response would take just as long to come back. In the worst-case scenario, a full exchange of information could take nearly an hour. This delay removes the possibility of real-time guidance, intervention, or troubleshooting from mission control. On Earth, complex operations such as rocket launches, landings, and system diagnostics rely heavily on teams of experts monitoring every parameter in real time. If something begins to go wrong, engineers can immediately analyze the data, suggest corrective actions, and guide astronauts step by step through emergency procedures. This safety net is a critical part of modern spaceflight. On Mars, that safety net disappears. Astronauts must make decisions independently, often under extreme pressure, without knowing whether their choices align with what experts on Earth would recommend. This becomes especially dangerous during time-sensitive operations. For example, landing a spacecraft on Mars involves a sequence of events that unfolds in just a few minutes, often referred to as a high-risk phase of the mission. By the time mission control on Earth receives data indicating a problem, the spacecraft has either already landed safely or crashed. There is no opportunity to intervene mid-process. The same limitation applies to launching from Mars. Ignition, ascent, and orbital insertion must all be executed autonomously, with no real-time corrections from Earth-based teams. The delay also complicates troubleshooting and maintenance. Imagine a critical system failure occurring on Mars, such as a malfunction in the fuel production unit or a fault in the ascent vehicle. Astronauts would first need to diagnose the issue themselves, then send detailed information back to Earth. Engineers on Earth would analyze the data, develop a solution, and send instructions back, a process that could take hours or even days for a single iteration. If the initial fix does not work, the entire cycle repeats. During this time, valuable resources such as oxygen, power, and time continue to be consumed, increasing the pressure on the crew. Another layer of difficulty arises from the complexity of modern spacecraft systems. These systems are highly specialized, often requiring deep expertise in specific fields such as propulsion, electronics, or software engineering. It is unrealistic to expect a small crew of astronauts to possess expert-level knowledge in every domain. On Earth, large teams of specialists collaborate to solve problems, each contributing their expertise. On Mars, astronauts must act as generalists, attempting to handle a wide range of technical challenges with limited support and incomplete information. The psychological impact of this isolation cannot be ignored. Knowing that help is not immediately available can increase stress and affect decision-making. In high-stakes situations, even small delays can feel overwhelming, and the burden of responsibility falls entirely on the crew. This isolation is not just physical but operational, as every decision must be made with the understanding that there is no immediate backup. Communication delays also affect navigation and coordination with spacecraft in orbit. Precise timing is required for rendezvous maneuvers, and any miscalculation could result in missing the target entirely. Without real-time updates, astronauts must rely on pre-programmed sequences and their own calculations, increasing the risk of error. All of these factors transform Mars missions into largely autonomous operations, where success depends on systems and crews functioning flawlessly without external assistance. The inability to receive immediate help or guidance turns even minor issues into potentially mission-ending problems, making the idea of a safe and reliable return far more uncertain than it might initially appear. Human survival on Mars is not just a matter of building a shelter and supplying oxygen. It involves confronting a combination of environmental threats that continuously act against the human body and mind. One of the most serious dangers is radiation. Unlike Earth, which is protected by a strong magnetic field and a thick atmosphere, Mars lacks both. This means that cosmic rays from deep space and solar radiation from the sun can reach the surface with far greater intensity. Prolonged exposure to this radiation can damage DNA, increase the risk of cancer, and potentially affect the central nervous system. Even with protective habitats, astronauts would still accumulate significant radiation doses over time, especially during long missions that could last years. The physical environment itself is equally hostile. Temperatures on Mars can swing dramatically, often dropping to around -80 degrees Celsius or even lower near the poles. Such extreme cold affects not only human survival, but also the performance of equipment and life support systems. Materials can become brittle, seals can fail, and batteries can lose efficiency. Maintaining a stable, habitable environment inside living quarters requires constant energy and flawless system performance. Any disruption in heating, pressure control, or oxygen supply could quickly escalate into a life-threatening situation. Air and water, the most basic requirements for life, are not readily available in usable forms. The Martian atmosphere is composed mostly of carbon dioxide, with only trace amounts of oxygen. This means that breathable air must be generated artificially through life support systems, which must operate continuously without failure. Water, while present in the form of ice beneath the surface, must be extracted, purified, and recycled with extreme efficiency. Every drop becomes valuable, and any loss or contamination can have serious consequences. Unlike on Earth, there is no natural backup, no rivers, no rain, no ecosystems to fall back on. Isolation adds another layer of difficulty that is often underestimated. A Mars mission would require astronauts to live in a confined environment with a small group of people for extended periods, potentially years. They would be separated from family, friends, and the broader human experience, with only delayed communication connecting them to Earth. This level of isolation can lead to psychological stress, including anxiety, depression, and interpersonal conflicts. Even minor disagreements can become magnified in such a confined and high-pressure environment, affecting teamwork and decision-making. The monotony of daily life on Mars also plays a role. The landscape is barren and unchanging, with no vegetation, no weather patterns like those on Earth, and no variation in scenery beyond rocks and dust. Over time, this lack of stimulation can impact mental well-being. Humans are naturally adapted to dynamic environments, and the absence of such variation can lead to a sense of detachment or reduced motivation. Limited resources further intensify these challenges. Food must either be brought from Earth or grown in controlled environments, both of which require careful planning and management. Growing food on Mars involves dealing with poor soil conditions, limited water, and the need for artificial lighting and controlled atmospheres. Any failure in these systems could reduce food availability, creating additional stress and risk for the crew. Medical emergencies present another critical concern. On Earth, advanced medical facilities and specialists are often just minutes or hours away. On Mars, astronauts would have to rely on limited medical supplies and their own training to handle injuries or illnesses. Complex procedures, or unexpected conditions could quickly become life-threatening without proper support. All these factors, radiation, extreme temperatures, limited air and water, isolation, psychological strain, and scarce resources, combine to create an environment where survival itself is a continuous challenge. Living on Mars is not simply about enduring one or two difficulties, but managing a constant interplay of risks that can affect both the body and the mind simultaneously, making long-term habitation and the prospect of a safe return significantly more uncertain. Any mission to Mars that includes a return journey cannot rely on improvisation or mid-course corrections in the way many Earth-based operations do. Instead, it must be planned with extreme precision years in advance, where every detail is calculated, tested, and locked in long before the astronauts ever leave Earth. This level of pre-planning is not just a preference, but a necessity, because Mars missions operate within strict physical and orbital constraints that leave almost no room for flexibility once the journey begins. The positions of Earth and Mars relative to each other change constantly as they orbit the Sun, and the most efficient travel opportunities, known as launch windows, occur only about every 26 months. Missing one of these windows doesn't just cause a delay of a few days or weeks, it can push the mission timeline back by more than 2 years. This timing constraint affects every aspect of the mission, especially the return journey. The spacecraft that will bring astronauts back to Earth must be ready to launch from Mars at exactly the right moment to align with Earth's orbit. If the timing is even slightly off, the spacecraft could miss its trajectory, requiring additional fuel to correct the course, fuel that may not be available. Because of this, mission planners must calculate trajectories, fuel requirements, and system performance with extraordinary accuracy years ahead of time, accounting for countless variables such as gravitational influences, orbital mechanics, and even minor uncertainties that could compound over long distances. The need for zero margin for error becomes even more critical when considering how many interconnected systems must work together perfectly. The return mission depends on the successful operation of life support systems, fuel production units, communication systems, navigation software, and the ascent vehicle itself. If any one of these components fails or performs below expectations, it can jeopardize the entire mission. Unlike on Earth, where redundancy and rapid intervention can often compensate for problems, Mars missions must assume that no external help will arrive. This means that every system must not only function correctly, but also maintain that performance over long durations without degradation. Another layer of complexity comes from the requirement to pre-deploy essential resources. In many mission architectures, the return vehicle and its fuel are sent to Mars ahead of the crew, sometimes years in advance. This approach is intended to reduce risk by ensuring that the means of returning home are already in place before astronauts commit to the journey. However, this also introduces new uncertainties. The pre-deployed systems must survive the harsh Martian environment for extended periods, remaining fully operational until the crew arrives. If any issue arises during that time, such as mechanical failure, environmental damage, or unforeseen degradation, there is no opportunity to repair or replace the system before it is needed. The concept of zero margin for error also extends to human factors. Astronauts must follow mission timelines with strict discipline, as even small deviations can have cascading effects. For example, delays in surface operations, resource extraction, or system maintenance could interfere with preparations for the return launch. Since the launch window is fixed, there is little to no flexibility to accommodate setbacks